Hello everyone, my name is Alex Fallen. I'm from the Efficient Computing Laboratory at Texas State University in San Marcos, and I will be presenting a simple, fast, and GPU-friendly Steiner-Tree heuristic today. First, I want to go over some background. What exactly is a rectilinear Steiner minimum tree? I will demonstrate using these three examples. The leftmost example is a normal minimum spanning tree that we've all seen before. We connect the points 1, 2, and 3 with the minimum edge length possible. The middle example is a Steiner minimum tree. Steiner trees can reduce edge length over an MST because they can add these special points, shown here in green, called Steiner points. These Steiner points allow for edges to share some of the length from one place to another, and in this case, 1, 2, and 3 are meeting in the middle, therefore decreasing the edge length over the full MST. If we add the additional constraint that all edges must be either horizontal or vertical, and in this case, due to a manufacturing requirement, we get the rectilinear Steiner minimum tree on the right. 1, 2, and 3 are connected with only horizontal and vertical lines through Steiner point S to create a full spanning tree. These rectilinear Steiner minimum trees are what SFP computes. Very large-scale integration, or VLSI, is a huge domain with many complex steps. Rectilinear Steiner minimum trees are used in the global routing substep of the signal routing step. In this step, you are connecting the output of each logic gate to the input of the logic gates that require it within the chip. Each chip has many of these gates to connect. The output of one gate that needs to be connected to the input of the other gates is called a pin net, shown here. Collections of these nets are called net lists, and these net lists are the input that are fed to our heuristic. There are three main reasons that we want a minimal wire length. First, when we reduce wire length, we reduce the power loss on the chip, which makes more efficient chips. Second, any additional wire length along the critical path will add latency to any operation that uses that path, so by reducing wire length we can create faster chips. Additionally, by reducing wire length, we potentially create more space on the die to increase chip capacity. Now I will introduce our simple, fast, and parallel heuristic, hereafter called SFP. You can see a diagram showing a Hanon grid on the right side of this slide. Our SFP heuristic is based on the observation that the center point of any 3x3 Hanon grid is always either the only Steiner point, as shown on the right, or already a pin in the net, as shown on the left. In both cases, the solution is to directly connect the non-center point pins to the center point. What's cool about this is that the coordinates of the center point can be obtained very rapidly from the coordinates of the three pins. Many CPUs and GPUs already have machine instructions to commute the minimum and maximum of two values, meaning that they only need to execute 4 instructions to find the median of 3. This extends to show that to find the median point of any 3 pins, we only need 8 machine instructions. The heuristic uses the prior 3x3 grid approach directly on 3-pin nets to find the optimal solution, and conceptually applies the idea to larger nets by processing them in this way. First, we compute the MST of all pins in the net. For each connected pin triple, we compute the median point. If the median is unique, or separate from the given pins, we consider it as a potential Steiner point. We add the best Steiner points to the tree, and we repeat until no Steiner points are added. It's important to note that we only actually compute the MST once per loop because it requires quadratic time, while finding the median points of all of the 3-pin tuples only requires linear time. Now I will step through the heuristic with you. First, we want to compute the MST of all pins in the net. We do this on this ABCDEF pin net, and the dotted lines represent the rectilinear L connections as shown in the example at the beginning of the presentation. Next, for each group of connected 3 pins, compute a median point. So S1 through S4 are the computed median points, where S1 is the median for DEF, S2 is CDE, and so on. Next, we want to add the best Steiner points to the tree. Of these potential Steiner points, S3 conflicts with S2 and S4 because it shares an edge with both points. However, it provides the most length savings and is therefore included in the tree. S1 conflicts with S2, but provides less length savings and could not be included in the round, And of course, S2 is not included because it conflicts with S3 and provides less savings. Now, we repeat this loop until no Steiner points are added. As mentioned in the previous slide, only one Steiner point was able to be added in this round. Its vertex, G, is shown in red. The MST is regenerated with the same rectilinear L routes being represented by these dotted lines. This is the input set for the next round. Now we regenerate Steiner points. We see that S5 through S7 have been regenerated. As you can see, we actually generated one potential Steiner point that coincided with a vertex that already exists. In this case, it's coinciding with G. It's automatically excluded, we don't even look at it. You can also see, because they're highlighted in red, that S7 and S5 are marked to be included in the next round. Now those two marked Steiner points are included in the tree and we regenerate the MST. After regenerating Steiner points, you can see that we've actually only generated a single viable Steiner point. After adding that last Steiner point J, we're done with the tree. There's one dotted line which represents an L route. That could go either up or down, it doesn't matter because it wouldn't affect the total length of the tree. Like many heuristics, SFP does not guarantee the resulting RSMT will be optimally short. Naturally, we wanted to know to what extent the suboptimality is. We know that our upper bound is at most 1/2 because we start from an MST. An MST has been proven to have an upper bound of 1/2 above the optimal solution. Because we only add Steiner points that improve our wire length, we can also include this 1/2 upper bound. Through observation, we found that the worst case we ever saw on a single net was 1/3, which is shown in this diagram. Epsilon, which is less than A in this example, causes the MST to create the pattern shown on the left. When we apply our heuristic, no Steiner points can be created that are distinct from existing vertices. The optimal solution on the right requires a Steiner point. This means that our solution produces a length of 4a plus epsilon, and the optimal solution is 3a plus 2 epsilon. If we take the limit as epsilon approaches 0, which is the worst case, we see that our heuristic causes 4/3 of the wire length of the optimal solution, i.e. a 1/3 suboptimality. In this portion of the presentation, I'll be covering some of the most pertinent related work. The batched iterated 1 Steiner, or BI1S heuristic, starts by computing all optimal Steiner points. It then finds a maximal independent set of these Steiner points that shorten the wire length without reducing the MST cost savings of any of the other points in the set. These Steiner points are incorporated in a single batch. This process repeats until there are no more Steiner points that result in savings. SFP follows the same high-level structure of computing possible Steiner points, eliminating useless and conflicting candidates, and iteratively adding the remaining candidates in batches until convergence is reached. However, SFP uses a new and very different heuristic for identifying the possible Steiner points. GeoSteiner employs a two-phase exact algorithm for creating full Steiner trees. It first generates a small set of full Steiner trees and then concatenates them using an integer programming formulation solved by branch and cut. What's really cool about GeoSteiner is that it will always produce the optimal RSMT for any pin net. Flute has offloaded the work of computing the optimal Steiner tree for all net sizes below 10 pins. These pre-computed solutions are stored in a lookup table that is referenced for any net that is sufficiently small. For pin nets that are too large for the lookup table, Flute breaks down the nets recursively and then solves them with the lookup table when the problem size is small enough. It's important to note that this relatively fast approach is what is commonly used in industry for RSMT generation. SALT is a special heuristic because it allows for a trade-off between signal latency and total tree length. When targeting signal latency, SALT attempts to minimize the highest latency from one source to a sink. It may even sacrifice some wire length to do so. When targeting wire length, it only attempts to lower the total wire length of the entire RSMT. To achieve this goal, it uses a shallow light tree structure that allows for a smooth trade-off based on the parameters set by the user between these two parameters. For the purpose of evaluating, we chose to configure for the lowest possible tree length, as that's the parameter that the other heuristics target. This slide shows how the related works compare relative to each other. At the top we have speed, where Flute is the fastest, followed by Salt, then BI1S, then GeoSteiner, which is an exact algorithm, being the slowest. You'll notice that the wire length chart is actually the inverse of the speed chart. GeoSteiner, being an exact algorithm, produces the best wire length, followed by BI1S, then Salt, then Flute, which uses the lookup table and the recursive breakdown. In this section, we will talk about how SFP is parallelized on both the CPU and the GPU. Because a net list typically has many nets, but each individual net typically only has few pins, we opted to parallelize SFP across nets in our OpenMP implementation for multi-core CPUs. In other words, each thread applies the heuristic to a separate set of nets by running the algorithm on each net. Since nets require different amounts of processing time, we used a dynamic schedule to balance the workload. As soon as a thread is done with one net, it attains the next net from the work list. This procedure repeats until all nets have been processed. We saw poor performance with parallelization across nets in CUDA. Because of this, we parallelize things a little bit differently than our OpenMP code. While we still use a dynamic schedule, we included specialized code for the 2 and 3 pin nets because they can be done extra fast using machine instructions as mentioned earlier. We parallelize the net list by dividing the nets up between the warps and assigning the pins in the nets to the threads in the warp. We targeted the inner loop of Prim's MST computation due to a loop carry dependency in the outer loop and performed the search for the closest pin that is not already included in the tree in parallel at the warp level. For processing the edge pairs, the highest achievable distance savings for each edge is recorded at the warp level using an atomic max, and the threads then concurrently process the pairs of edges to see which ones agree on Steiner points. Those Steiner points are then added to the tree. In this section, we will discuss how our heuristic compares to the related works in terms of speed and wire length. For methodology, we used a system that has an NVIDIA Titan V GPU with 5,120 processing elements, 80 SMs, 12 gigabytes of memory, and we used NVCC version 11. The CPU in this system was an AMD 2950X, which has 16 cores at 3.5 GHz per core, and GCC 9.3. It's important to note that the CPU has hyperthreading enabled. The codes we compared to are shown in this table. We compared to BI1S, Flute, GeoSteiner, Salt, our serial code, our OpenMP code, and our CUDA code. These are the inputs that we tested all codes against for comparison. They are from the ISPD 2008 Global Routing Contest. You can see that the number of nets vary greatly from a small number of nets to quite a large total number of nets. All inputs have at least one net with more than 256 pins per net. As downloaded, many of the related works cannot operate on nets with more than 256 pins, so for fairness, these nets were truncated to 256 in all following comparison tests. The average pins per net is always above 3, which is important to note because not all nets are just the small net size cases that are trivially easy to handle. The largest nets end up being many thousands of pins, which SFP is uniquely equipped to handle, as will be mentioned towards the end of the presentation. These are the throughput results on all the tested codes. Larger is better. On each tested input, our parallel GPU code is the fastest, our parallel CPU code is the second fastest, and our serial CPU code is the third fastest on all inputs with one exception. Flute is a similar speed to serial SFP, but is still a little bit slower. In absolute terms, our GPU code ran between 55 million and 250 million nets per second. It offers nearly 2 orders of magnitude in speedup over Flute, 3 over Salt, more than 3 over BI1S, and nearly 4 over GeoSteiner. You'll notice that this is the same speed pattern mentioned in the related work section, with the addition of our codes in the fast category. As you can see in the GeoMean, the fastest code tested was our GPU code, followed by our CPU parallel code, and then our serial CPU code. It's important to note that the slow GeoSteiner code is slow because it is optimal. These are the wire length results. The total wire length of all nets in the input is listed in the GeoSteiner column because GeoSteiner is an exact algorithm and produces the best possible wire length. The rest of the columns report the increase in wire length over GeoSteiner. Only one column exists for SFP because all three implementations are deterministic and produce the same answer. For this table, percentages closer to 0 indicate a lower wire length and are therefore better. BI1S is the best behind GeoSteiner, followed by SALT, followed by Flute, and then SFP. While SFP is last, the difference in wire length for all algorithms are small. BI1S only yields an increase of 0.08%, SALT 0.1%, Flute 0.18%, and SFP 0.55%. In other words, for all tested inputs, our solution is about 0.5% longer on average and never goes above 1% longer. We believe that this is a small increase in wire length as the solution yields that answer 8,100 times faster on average compared to GeoSteiner. Compared to the commonly used Flute approach, we are only 0.38% longer and produce a solution 86 times faster. We wanted to look at the wire length and throughput for different net size ranges by themselves. To this end, we classify nets with 2 to 3 pins as small, 4 to 9 pins as medium, and 10 to 256 pins as large. Both tables report the geometric mean over all inputs. For wire length, we follow the same relative to optimal reporting as the previous wire length slide. For the throughput results, on the small nets, SFP outperforms all other approaches. Flute and BI1S are notably high in this category, with BI1S beating SALT. We see weak scaling for the OpenMP version of SFP in the small net category because of how fast serial SFP is. This speed can be attributed to the speed of the median calculations. For the medium range, Flute outperforms serial SFP. This is likely due to the lookup table being very fast. Both parallel versions of SFP still outperform serial Flute. On the large nets, where Flute no longer has a pre-computed solution, Flute falls behind SFP and SALT. SALT is particularly notable here because it outperforms serial SFP and Flute on these nets. For the wire length results, all tested approaches are optimal on 2 to 3 pin nets. Only Flute, SALT, and GeoSteiner are optimal on the medium nets, and only GeoSteiner is optimal on the large nets. The trend for all approaches except for GeoSteiner is solution quality getting worse as net size gets larger. Nonetheless, they all produce solutions that are close to the optimal wire length. As mentioned in the input section, large nets exist in all of the ISPD inputs. These nets are generally too large to be handled by the other codes. As downloaded, none of the related works support nets of these sizes. To show a real-world example of a large net, we ran SFP on the largest net in the Adaptec 5 input, which has 9,863 pins. We present the results here with one of the dense areas blown up to provide more detail. It took serial SFP just 1.1 seconds and 7 iterations to compute the solution, which is 6.5% shorter than the pure MSD solution for this input. To summarize, today we presented SFP, a simple and fast RSMT heuristic. It provides a speedup of 86 over the commonly used Flute and 8100 over GeoSteiner at the cost of 0.38% and 0.55% wire length respectively. SFP can handle very large pin nets as shown in the last slide, and our serial, CPU parallel, and GPU codes are all available at this URL. Thank you for your time, and have a great rest of your day.